Hi, welcome to lecture 30 of Quantum Physics for Non-Physicists, and I'm recording this. It was very optimistic of me. I'm recording this on the 19th of January, 2021. Again, as we said before, like the things I'll talk about today are good there for completeness, but they will not be in the exam. Okay, so what we'll do today is continue. So we talked about angular momentum, and now we'll talk about applying this to physical problems where we have a central potential, so something that only depends on the distance to some center. And then in particular, we'll talk about the hydrogen atoms, and we'll see how people derive the different energy levels and so on. And we will use towards the end a little trick that I put here explicitly because it's a different part of the book. So of the Schumacher and Westmoreland book, most things we'll talk about today are in chapter 16, except for this one trick is in chapter 15. And our daily analogy today has to do with going to the gym and weightlifting and strength training. In that everyone likes to have done it, but in the moment, I doubt most people enjoy the actual process of lifting these weights, but you have a goal in mind. You know, of course, you can admire the theory of, oh, you need to put your hands in this way or push with your feet like so. But the actual work you do is not that much fun. Okay, but of course you like the results. So in the same way, some of the maths involved here are very difficult, not that enlightening, and just kind of tedious to do. Okay, so just like lifting. So we will not go into details through all of them, but again, you know, it's nice to have done them because the results are very important. In particular, when you find out, oh, so this is how the hydrogen atom works, and this is how we do it. But we'll be here more like coaches, telling people how they should lift, and then let someone else do the actual work. Okay, it could be a computer, or it could be just a physicist that actually solved these differential equations 100 years ago. Okay, so just to see where we are in the lecture, so this is kind of the end. We've done, well, just the basic formalism, then we did the dynamics, we talked about different types of uncertainty and how to model it, and finally we talked about spin. This was the theory part. Okay. In the applications part, so we talk about qubits, or the operators on qubits, then dynamics of qubits is so about rotating spins, how to do a measurement, how to implement a measurement as an actual physical evolution. We talked about entanglement, we talked about quantum circuits. Then in the continuous case, we talk about how to model a particle in space, like this continuous spaces, X and P, the commutator, 3D, wave packets, and so on. Then we saw some examples like the free particle, a particle in a box, how they behave. We looked at different types of potentials that a particle can feel, and we talked just a little bit about how these very idealized potentials can reflect something that happens in real life, right? The scattering, the reflection, the bound states, the tunneling, and so on. Good. Then we saw some applications where we spent quite a lot of time. So one was the double slit experiment, and the other one was the Stern-Gerlach experiment, where you actually couple two systems, and we couple the spin to the position or momentum degrees of freedom. And in the double slit, we did quite a deep analysis to see how this interference fringes actually occur and what happens if we, for example, measure which slit the particle went through, right? Then we talked about quantum thermodynamics as an application of all this uncertainty and modeling uncertainty in quantum theory. And the main reason why I wanted to include this in the lecture is because all of this this research is the most recent research that we're doing here, that we're talking about in this lecture. So everything, including what we do today, like the angular momentum, central potentials, and so on, this is 100 years old. Maybe some of the things about entropy are a bit more recent, but very, 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 very old in general. Whereas the things I talked about in quantum thermodynamics, like this protocol for Landauer's principle or the nano heat engines and so on, this is research that is still being published today. And some of the most important work in this area is only 10 years old or so. Okay, so my point here was to say that even with the knowledge that you have from this one lecture, you could already be doing state-of-the-art research. But then, of course, we have to go back to the mandatory topics. So we talked about spins and how to add spins, and about angular momentum. And today we're going to finish this with the hydrogen atom. Okay, there's much, much more to quantum theory. This is really just the very, very basics. Okay, I might do another lecture, as I promised before, with just the full treatment of a quantum heat engine, where you can see the Lindbladian and the evolution, the internal evolution at the same time. Okay, so where were we? Last lecture, we talked about the spherical coordinates and spherical harmonics, which were the eigenvectors of both total momentum and momentum in the z direction, right? So what we want, we're looking for these states, which can be characterized by two numbers, L and M, which are eigenstates of both Lz, so the spin angular momentum in the z direction with this eigenvalue M, and of L square, which is, remember, Lx square plus Ly square plus Lz square, right, with this eigenvalue. And of course, how to express this quantum state? Oh, I'm missing something here. So it's a 3D state. So a state that lives in 3 dimensions. So we have here r, theta, and psi as basis elements. And then the coefficient is given by the wave function. And we saw how to express the wave function in terms of like kind of the Cartesian wave function, right? Good. And then we saw that, so these wave functions that we're looking for, which are the ones that give us eigenstates of the angular momentum, that kind of three parts. One depended only on r, and this for now was free. Then we had this dependence on phi, which is this angle here. And this dependence is just this exponential, it's just a phase. And then we had this dependence on theta, which is this angle there. Okay, and these were these polynomials that we looked at. Okay, why does it have a special dependence on theta? It's just because we want them to be eigenstates of z, and z depends on theta and not on this at all. Okay, if we had chosen we want eigenstates of Lx, for example, then of course this dependence here would be more complicated. Okay, but we pick the easy one. Okay, that's why we parameterize the theta in this way. Good. Okay, I'll go through this relatively quickly. It's just to say, well, we found out how to express all these operators, both x, y, z in spherical coordinates, to see how they act on this wave function of spherical coordinates. And we looked also at the ladder operators that go up and down the different eigenstates, and also how to represent the total angular momentum. Right? So we'll take all of this as a given. And now we talk about central potentials. And these are potentials where, systems that have a Hamiltonian, where you just have this usual term, which is this kinetic energy. So it just depends on the momentum of the particle, for example, that you have interest in. And then a potential that now only depends on the distance to some center. Okay? One example that is very familiar to everyone is just gravity. Okay, where there you just care, for example, distance to the sun from the Earth's perspective. And the another one are just electric potentials, right? You have a charge in the middle and you have a charge down at a certain distance, and the force between them only depends on the distance. Okay. Good. Something that is not an example of this would be, for example, magnetic interactions, where there you do care about more things than just the distance between the two. Okay. So how do we treat these kind of things? So the first thing will be to see that this Hamiltonian commutes, like we promised before, it will commute with L square and with Lz. So that then we can take, well, the Eigen States of angular momentum are also energy eigenstates. And we know how to create all these eigenstates of angular momentum from all this treatment we saw before, right? It's just spin. Good. So how do we do this? First of all, what is p squared? Well, like we saw, it's this, right? So it's px squared, the tensor the identity in y and z, plus py squared, identity in the rest, plus z squared, identity in the rest. And we know how it acts on the Cartesian wave function, right? So we know it just takes the second derivative in all the coordinates. This is called the Laplacian. So all we have to do is to take this thing here and translate it to spherical coordinates. This is a very classic transformation. You've probably seen it in a different lecture. We will not do this here. If you want to do the method explicitly, it's exactly what we did in the last lecture with all these partial derivatives. Okay, so we let someone else actually lift this weight, and we get to the final result, okay? So this is just how, again, how the momentum acts on the spherical wave function. Good, on the, yes, wave function in spherical coordinates. Now, it is a bit ugly, and the only thing that matters here is that this term looks very familiar. I'll show you again, but this term is exactly only the way that L square acts on the wave function, okay, up to some constant. So let's go and see. So remember here, we saw this total angular momentum acts on the spherical wave function like so. Okay, and if we look there, it's exactly the same terms, except that there's this extra r square down there. The h square, the h bar square is from there, so it's not a problem. Okay, so then this means that we can try to, so that's this term here, right, that we're looking at. So we can try to rephrase this term here of the Hamiltonian as just putting there the L instead of writing this whole thing. Yeah. So there it is. How does the Hamiltonian act on the wave function in spherical coordinates? Well, it acts like the angular momentum square, the total angular momentum, plus this v of r that we don't know what it is yet, and then this term that was the leftover term kind of from before. Okay, that's the leftover term. So we just put it there. So what is interesting here is that we have one term that's L square, and everything else does not depend neither on theta nor on phi. It does not depend on the angles. So this only depends on r, 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 r here, and another r there. Yep. And we know that neither L square nor Lz depend on r. Okay, if we remember when we computed the angular momentum in spherical coordinates, all of this only depends on like this coordinates and multiplications by functions of theta and phi, right? All of them. R did not matter at all. Okay, but then what this tells us, well, if it does not depend on R, then it will commute with any operator that only depends on R, right? This will act like a constant essentially. Okay, so these two things will commute, they act on different spaces even. Okay, so then what do we deduce from here? Well, then this means that L square is going to commute with a Hamiltonian because, well, there's the parts that's some h bar that depends only on r plus L squared divided by r squared and some constant. Okay, and this whole thing. commuting with L squared. So of course it's going to commute, right? Every operator commutes with itself, and then what's left is just something that depends only on R. Okay. So there we go. And because Lz also commutes with L squared, it follows that Lz must commute with the Hamiltonian as well, right? For exactly the same reason. So this means that, as promised, the Hamiltonian, L squared, and Lz, they will share they share the same eigenstates. Okay. So now we're looking for these eigenstates. And we know, just like we saw before, that there's some function that depends on R, and then there's this kind of polynomials that depend only on the two angles. Okay, and these are fixed. We found how to compute them before. Okay, so in this, we saw that before this was free, but now, of course, that there's many terms here that depend on R, so this thing will no longer be free, and this is this is going to be the equation that we're going to have to solve, as we'll see in a moment. Okay, so we'll find an equation that will give us this thing. Okay, good. And so if you write down the final, if you write down the eigenstate equation, so you know that the Hamiltonian applied to this eigenstate will give you some energy eigenvalue, which we don't know yet. Okay, we just put E here. And now if we apply this thing with the H acting like this on the wave function, okay, then I'm just putting something on the right side. So here's the E that, and this is the same thing as was before on the left, right? So this is just H acting on the wave function. Okay, so we've got this part here. And now what we know from here, well, we know this thing. We know how L squared acts on the wave function. We know that it gives us this little, eigenvalue, right? It gives us L plus 1 times H bar square, and the rest is just the constants that were already there. Okay. So we can replace this term here with this term there, which already simplifies our life, because now we just have kind of this derivative, this unknown term, and then this. Now the next step is to say, well, our function, like we saw, it's a term that depends on R times something that does not depend on R at all. Okay. So by plugging this in here, we can completely get rid of this term because it acts like a constant over here, right? Look, because nothing here depends on these other angles, right? So it's like you put this y here, y there, but it commutes with all the derivatives because it's just a constant, so you can kind of cancel it out. So at the end of the day, we have an equation that is only about R. Okay? It's not a simple equation yet, but let's just try to make it a little bit simpler. Okay, so we just reorder the terms a little bit. We put everything that has to do with the derivative on the left and everything that doesn't have a derivative to the right. Okay. So on the left, we have this double derivative, which is a bit annoying because you have ddr, and then there's an r square, and then a ddr again. We'll take care of this. On the right, we just have this kind of big constant, right? That we don't know yet. Well, this can depend on r, and there's an r square there. Good, so this is the differential equation that we'll be able to solve when we have explicit versions for, explicit examples for what this potential is. But maybe we can make some observations already. So of the quantum numbers that we saw before, of the angular momentum, remember we have L and M. Nothing here depends on M, right? We have L there, but nothing depends on M. So you know that R depends only on L. So we can write kind of R that depends on L. Okay, and the energy depends also, can depend on L, and it could depend on some other number, okay, which we don't know anything about. We don't know even if it's a discrete number or if it's a real number, but we're just going to call it N, okay? So that's what we're doing here. So then in particular, because this depends on the energy, it also depends on this number N, okay? So we put N and L depends on N and L, and the energy depends on N and L. Okay? So it's just a way to kind of index things. We're not adding any physics here. Okay. So what we want to do, don't be scared by this. So first we want to simplify this equation, and then we want to plug in like a specific central potential, and this will be our hydrogen atom. But let's see if we can simplify it a little bit before plugging in an actual potential, okay? So that's the equation, and we're going to try to simplify two parts of it independently. So this term on the right, and then we look at this term on the left. Okay. So for this term on the right, well, we're just going to say we'll replace it with the energy minus some effective potential, where this effective potential is going to be VR minus this thing, minus this term here, okay? It's nothing special, it's just a change of variable. But the important thing here is that if we look at it, well, this term will explode when we go to, when r goes to 0, because it depends on r squared, which means that this term here is going to be huge when r goes to 0, and this will give us some boundary conditions for the wave function at the end. Okay, we will set essentially that the wave function must be 0 at the origin and 0 at infinity, like we did in other kinds of potentials, because we see this becoming very, very large or very, very, very small. But we will not look into this. So it's just so you know that there's a trick that physicists use sometimes. The other trick is to get rid of this annoying derivative here, where we have ddr r squared ddr of something. You just define a new function, which is just taking the function we're looking for, this r, and just multiply it by the radius, by the small r. Okay? And then if we go and compute this derivative, I will skip the details here. I mean, it's really just going painstakingly computing this, all these derivatives. We will see that it gets rid of this term here, because we can write the whole thing as 1 over r, and then the dr square of the new function. Okay. And this allows us to rewrite the whole thing. So we really just simplified this a little bit by changing variable. Okay, and this is it's really just a trick. Okay. So we had this big thing there, and now we simplified it to this. So we also replaced this with that there, and here's the 1 over r, and it kind of cancels out because we assume that r is always larger than 0. We're not going to compute the wave function at the exact center. We're just going to say, well, for r larger than 0, then these things can cancel out. Okay. And here, again, don't worry about the details. If you want to really get into this, there's several books that explain this much more precisely, but here's kind of more of a quick and dirty, high-level view of what is done. So with all this, we simplified as much as we can for now, because now we can cancel these r's, and we're left with this kind of equation, which is a very simple equation. Look, it's just a constant times the second derivative equals something, some potential energy, times the function itself. So if you know the value of this for fixed r, then you know how to solve things. Because if you remember, for example, our stationary states in 1D. Okay, so there you had just a particle on a line, x, and you had this p square was just the x derivative square. There could be some potential, like we saw some examples, right? And the equation was exactly the same, right? So we had the second derivative on the left, and on the right we had energy minus the potential. Right? So all these examples that we saw of bound states in 1D, they work exactly the same for 3D examples if your potential only depends on the distance to the center. Of course, the difference is that then your wave function will also have this radial component, the angle components that we saw before. But essentially, what this tells us is that we have the same differential equation as we had before, so it will have the same solutions. If this effective V was of this shape, then we'd have the same solutions as we saw for the particle in the box. But of course, in the case that we're interested in, it's not going to be that easy. This potential is going to have a more complicated shape. Okay. So let's just summarize what we have so far so we can move on. So we have a Hamiltonian of this form where V depends on R. We have this energy eigenstates that we're looking for, which we now know depend also on some number n, but the energy itself depends only on n and L and not on the z component of angular momentum, right? We saw that the wave function is of this form. We are looking for these wave functions because these are the spherical harmonics polynomials that we've already looked at. Okay, so we know what these look like. And this, we just wrote it as some other new function divided by R, and now we're looking for this thing here. And we had some constraints, so we want it to be 0 at the origin, and in fact we also want this whole thing to be 0 at infinity. So we don't want, if you think about a hydrogen atom, you don't want this electron to be possible to find this electron infinitely far away from the nucleus, if you're talking about a stable atom, at least. And then we found that this is the equation we're trying to find out. And some things I skipped over was things like, well, we need to normalize this whole thing. And because of the way we defined the spherical harmonics, this turns out that the normalization condition will translate to, well, this little function here needs to be normalized. By the way, there was a typo about this. The normalization constant in the previous lecture, I went and fixed the handwritten notes. Good. And this effect of potential is just the potential minus the part due to angular momentum, right? Where you have the R squared dependence. Very good. That's what we have so far. And now we can try to plug in a specific example. So we'll talk about the hydrogen atom. And so I'll give you a cartoon, which is not a realistic depiction, okay? So the idea is that in the hydrogen atom, you have typically just one proton in the center. Sometimes you can also have a neutron, which has no charge. And you have an electron around it, okay? And of course, this picture here is not realistic because this is the picture if your R function was very, very neat, like 0, 0, 0. Oh, I'm a little bit, and now I'm 0 again to give this kind of depth. Of course, what we'll find is that the wave function's amplitude will go something like this. But okay, but what matters here is that we have this electron going around the proton. It's oscillating. And what are the relevant parameters? Well, they have an electric charge, which is very, very small. So this is in coulombs. Doesn't matter exactly what this unit is, but it's very, very small. But normally we just call it, instead of writing this number all the time, we just call it one electron charge, okay? And the electron, in the electron case, it's negative, so it's -1 electron charge. Yep. And the proton has +1 electron charge. Okay, so they have exactly the same charge, but with opposite signs. So they attract each other. And we'll see what the effect is. Good. Now, the other important thing is that the mass of the electron is much, much smaller than the mass of the proton by over a factor of over 1,000. Okay. So we do this approximation where we're going to neglect the effect of the electron on the proton, and we'll consider only the proton to be fixed. So it's like we go to the reference frame of the proton, and we just think of this electron going around it, feeling the electrical potential. So in the same way that, if you want to do a proper calculation about gravitation, and you have a very large body like the Earth, and then you have yourself, normally you don't need to consider the effect of the pull that you have on the Earth, but you consider only the pull that the Earth has on you. Okay? This can backfire if you're, for example, maybe not you, but something as large as the moon. Then of course the moon has some effect on Earth with the tides and so on. But in this case, for a first approximation, we're just going to the reference frame of the proton. So we are sitting here in the middle. This is the center of my coordinate system. R is going to be the distance to the electron. And we're going to think, well, how does the proton see the electron? Okay. What's the electric potential that this electron feels just from the presence of the proton? In the same way that we think, well, how do you feel the gravitation effect of Earth on you? Okay, so this is the formula in general for the electric potential between two charges, Q1 and Q2, at a distance r. So it's just the product of the charges divided by the distance times a constant, which is a Coulomb constant. It doesn't matter for now. In the case of hydrogen, well, these charges are the same. They are just E, but one of them is the negative of the other, so we get this minus sign. Good. Now, this was the case in classical physics, and it could all be that in quantum physics, if you look closely enough, then this is not the exact formula. Okay? In fact, there's a whole field of quantum electrodynamics. But what matters is that we try this, we see what results we get, we compare to experiment, and then we decide if we're happy with this or not, or if we need to come up with a different model. So this was the model people knew from classical charges, and we tried to apply it here. And it turns out it works very well. Good. So what kind of questions do we want to ask? Well, one is, well, what's the size of an atom? What's the average distance between the electron and the proton, even if we know that this is not the exact picture? Another one is, well, what's the energy spectrum? So what are all these energy levels? And this is a question that you can answer experimentally. So essentially, you kind of, I'll talk about this at the end, but you shine lots of different light at the atom. So this electron gets excited to higher energy levels. And then when the electron relaxes, it will emit a photon, and you can measure the energy of this photon. So you learn like this gap between every two levels. We'll talk about this at the end. So because, historically, what people had was this from doing the experiments. They knew what these energy gaps were, and they did not fit the theory they had at the time. So in the theory they had at the time, the classical or semi-classical theories, it looked like this energy spectrum should be continuous. Okay, in the same way that you can have planets around the sun and you can put them at any distance, right? At a continuous distance, and it still work out. And the other thing that they expected was that from all the models, this electron should just kind of spiral out of control towards the nucleus, okay, which clearly doesn't happen in real life. So the theory that existed did not fit the experimental results. And the other thing will be, what is the shape of all this eigenstates? Good. So now what's the goal? The goal is now to find, remember, we have this differential equation, we're looking for this function. Okay. So now all we have to do is to replace this thing here with this, with the potential that we have, minus the term from the angular momentum. Now, if you look at it, it's not a simple equation. So on the one hand, we have a second derivative, then here we have a constant, and then we have a term that's 1 over r, and then a term that's 1 over r squared. Okay. So the rest, this is how like the physics kind of stops here. And now comes like lots of just tedious differential equation solving and using some kind of clever tricks that are obvious in retrospect to solve the differential equation. So we will skip this part. Okay. Essentially, if you want to, I did just for fun, try to plug this into, essentially Mathematica Wolfram Alpha to see what solutions it comes up with. And it's extremely complicated. So note that this is not the result. This is just a function m indexed by this and that. And one of the indices is itself another function. No, sorry, this is not one of the, this is just another function that has, again, a crazy index. But of course, that in reality, we have more constraints. So it's not as simple, it's not as basic as this equation here. We know that all these coefficients are positive, right, up to the sign. We know this limits that we want to impose, the physical limits we want to impose on the wave function. We know it needs to be 0 at 0 and at infinity, and so on. So if you want to see a derivation, like a physics derivation, which means we use all these tricks all the time, you can see it in the book, but we'll just summarize the results. The kind of relevant part is that in order to stop things from exploding, meaning being able to find this hydrogen infinitely far away from the atom center, then we need to impose some constraints on some mathematical series that appears there, and that's what kind of will fix this number n. Okay, so the physical constraints will impose some constraints on the solutions. It will not be just this crazy thing here. It will have very specific values, and there will be some constraints on n. So let's just see what these constraints are. First one is that n is strictly larger than L. So therefore, it's always a positive number that can start. So we saw that L can be 0, 1, 2, and so on. This means that n must start at 1. Yep. Okay, so if we count the number of eigenstates, so we have for n equals 1, there's only 1 with L equals 0, right? Because of this constraint. At n equals 2, there's 2 options for L, so L can be 0 and L can be 1. If L is 0, there's only one possible value for the z component of the angular momentum, right? It can only be 0. But if it's 1, like we saw before for spin, that m can be -1, 0, 1. Right? Now we go up again, and now could also be 3. Well, now L can be 0, L can be 0, 1, or 2. There's only one state if it's 0. If it's 1, then again, there's like these 3 states. And if it's 2, then there's like 5 possibilities for m. Okay, so what we have here is like L, n, and here the number of states, the number of energy eigenstates. Yeah. The other result that comes out of there, of solving the differential equations, that the energy value does not depend on L, actually it depends only on n. Okay. And it's quantized in this way, so it's like a constant. Remember, this is the mass of the electron, this is the electric constant, the Coulomb constant, the charge of the electron, h bar, Planck constant, and then it depends on n in this way, which tells us what? Well, the state, there's a minus sign here, so the state of the lowest energy is when n is 1. So, okay, so this will be the ground state, and so energy kind of goes up like this, although the scaling is a bit different, right? So the scaling increases. But this also tells us if the scaling increases, if the energy of this is there and the energy of this is much further up, it tells that atoms will, we saw what the thermal state looks like. They like being close to the ground state. So most of the time, the atoms will be kind of in this region, unless you have very, very high temperature or excite them in some other way. Good. We can define a constant, okay, which is called Bohr radius. It's just like this little constants all multiplied. And we define it like this because then, it will turn out that the average radius on the ground state is precisely this. We'll see this later. And the other thing is that the radial component of the wave function that we're looking for, well, it turns out that can be written as a function of r over a. Okay, and what is this? So it's going to be a constant, which is its normalization, r over a to the L. So the larger the L, then this will become more relevant. Then 1 over n in the exponent of, the exponential of r over a 1 over n, and then some polynomial. And this polynomial, which has a name, Lagarde polynomial or associated Lagarde polynomial, shows up a lot in physics because it's a differential equation that represents kind of physical systems. This polynomial that also depends on r over a. Yeah, we'll see just some specific examples of what this is. Okay, so the first few eigenstates, they look like this. So we have n equals 1. There's only one option for L. There the R function looks like this. Okay, it's very simple. It's just like this exponential on r over a. So it goes this way. There's only one option for M, which we saw before. So L is 0, so M must be 0. And if you remember from previous classes, then the spherical harmonic with L0, M0 is just a constant. And this kind of states with L equals 0, they're called S orbitals. Okay? So if n is 1, this is called state S1. I'll just write it down here. S1. Yeah, this is going to be S2 or 2S. Yeah, I think that's more common, sorry. So this is 1s, this is 2s, this is going to be 2p. It's called p orbitals. Doesn't. Just so you know, if you talk to someone from atomic physics, they just call these different names to the different energy eigenstates, and they also call them orbitals. Okay? So what does this tell us? Well, in the ground state, then the wave function is kind of uniform, independently of the direction you look at. Good. Then for the next, so we have now n equals 2. There's two options for L. It can be 0 or it can be 1. If it's 0, the radial wave function looks like this. So now it's a bit more complicated here. We have this term here. And again, if L is 0, then M is 0. So we have again this kind of S orbital. Now, the other option for n equals 2 was L equals 1. There, this radial wave function looks like that. I know this is a bit boring, but I just wanted to tell you that there's two options for the spherical harmonic, depending on M. So M can be 0, or there's three options. M can be 0, it can be +1 or -1. And we saw in the previous lecture what these look like. And for L equals 1, these are called the p orbitals, and so on, right? There's a method to compute all the eigenstates. But what does this tell us? Hi. So sorry about that. I got interrupted. Someone rang at my doorbell and I had to stop for the day. And now we're restarting. It's a new day. And let me just recap what we did. So we just looked at what some of the eigenstates are for the first few energy levels of the hydrogen atom, right? And for now, just looking at this, it tells us a little bit. So we can see, for example, here, by looking at the first energy eigenstate, which as we saw is called the 1s orbital. So 1 from the energy level number 1, and s because it's what atomic physicists call it when L equals 0. So what we have here, well, we know that it's uniform again along all angles, and that it kind of just decays with R. So if we look from the distance to the center, then you'll see something like this. And if you look from above, like here's the atom, it's kind of uniform, right? In this case here, for example, where we have some angular momentum now, so L equals 1, N equals 2, so it's a 2p orbital, then you don't have this uniform kind of density of the wave function over all angles, but it depends on theta, and it also depends, or for m equals plus minus 1, it also depends on this angle phi, right? Although only by a phase in this case, if you only have one electron. But what does this tell us? We want to evaluate some quantities, as we saw before, like we know what the energy eigenstates are, but we want to know things like what's the average size of an atom, depending on in what level it is. So for this, we're going to learn a trick, okay? And your experience with the next part of the lecture is going to be, why are we doing this? Why are we doing this? Why? Okay. Yeah, but it's a trick that in retrospect you can see, yeah, it can be useful, but it's not obvious at all how to get there. It's called the Feynman-Hellmann theorem. And it's useful if you want to compute some average quantities like the average radius for energy eigenstates in particular. So what we need to know already the shape of the Hamiltonian, which we know, we have the expression for the Hamiltonian, and for the energy levels. Okay, the energy eigenstates is not really important, but the energy eigenvalues, then this, you should know the expression for this. Okay. And you need the, all three things, so the Hamiltonian, the energy, and the eigenstate, to depend smoothly on some parameter lambda. So I'll give you an example to show what this means. So for the hydrogen atom, we saw that the energy depends, is given by this thing here. So it depends discretely on n, and is a discrete number, so it's not one of these parameters, but it depends on the mass of the electron, on the electric constant, on the charge of the electron, and on the Planck constant. Okay, so if we go to the regime where h is not 0, then it depends smoothly on all of these constants, meaning that if we change mu by a little bit, then En would only change by a little bit as well. And the same is true for the Hamiltonian. We saw that you can write it like this, p squared divided by 2, the mass of the electron, minus this thing here. And this also depends smoothly on all the same constants, right? The h bar is kind of implicit because we know that it's inside the p when we apply the p2 wave function. So the kind of parameters that we'll be using is going to be parameters like these constants, which don't really change in reality and don't change smoothly. Like the charge of the electron is a fixed thing, but we will change them as a trick. So let's see. Then we will prove this relation here, and I will prove this relation in the next page because I want to show you first what we can do with this. So what we have here is, if we write the expression for the energy and want to derive it with respect to lambda, then this is given by the derivative of the Hamiltonian with respect to lambda, and then sandwiched by the eigenstate corresponding to the same energy E. The point of this, that you'll see that will be useful, is because these derivatives, as we'll see, they're quite easy to calculate, okay? Whereas doing this whole thing is going to be hard. So I'll show you an example of where this can be useful. So let's choose our parameter lambda to be the Coulomb constant, the electric constant K. And now let's just apply this formula. So we have the derivative of the energy with respect to k for some energy of some level n is given by, well, here's the sandwich with an eigenstate that corresponds to this energy. And here is the derivative of the Hamiltonian with respect to the same variable k. Okay, so we just replace here the En with the expression for this, and here the Hamiltonian with the expression of the Hamiltonian. Okay, we didn't do anything special. And now we take this derivative. So on the left, we have the derivative in order to k of k squared, and everything else does not depend on k. So that just gives us 2k times everything else that was there. Now on the right, we have the derivative of 2k of these two terms. This does not depend on k, so the derivative is going to be 0. And this one is just a derivative of k times a constant, so it's just this thing, right? Okay, so now we're just going to simplify a bit more. So we have e squared here on this side and e to the fourth there, so we get only e to the square, and the minus sign also cancel each other. So now we have this expression here. And this thing here, if you remember, this was this is the inverse of this quantity that we defined before, the Bohr radius. Okay, if we go back, here it is, right? Okay, so we just replace this with a. So now we have that the average of this observable, that's 1 over r, for an energy eigenstate of the hydrogen atom, is given by a times 1 to the n square. And now we've used a trick that works sometimes, and you have to be careful with the mathematical subtleties of this. But if we just say that 1 over r the observable, if we can make bring the observable down here, if we can do this, then we reach the conclusion that then the average r, so the average distance to the center of the atom, so between the electron and the center of the atom, for an energy eigenstate of numbers n, l, and m, is precisely the Bohr radius times n squared. And this is a result that turns out to be right. So this tells us that an atom is kind of larger the more excited the electron is, and that this depends on n squared. And it also justifies a posteriori why we call this constant a radius. It's because, for example, for n equals 1, if the hydrogen is in the ground state, then the average radius of the atom is going to be just a. Okay, good. So the way, as you see, like the way this trick works is to just then choose the derivative to something that is easy to take, and see that here we end up with something nice. So for example, if we had chosen the derivative to mu, maybe we would find out, on this side it would disappear. So maybe we would find out something about the average value of p squared. So again, there's some subtleties with this. And if you want to actually apply this in real life, I advise you to read a bit more about this, but that's the idea of the trick. Still, we need to show that this is true. So we'll do this now. Okay. Now we know why it's useful. So let's just do it. So we start with what's the definition of E? Well, from the Eigenstates equation, you have the Hamiltonian E equals E times the same state, right? So that's what gives us this. So E is the eigenvalue associated with this state for this observable, which is the Hamiltonian. So we take the derivative of this. It should be the same as the derivative of this. And now we have a derivative of a product, right? So remember, this is a vector. It's like a row vector. This is a matrix, and this is another vector. Okay. Or in the continuous case, they are the generalized vectors and matrices, but it's the same idea for the derivative. So we need to have derivative of the first, so of the bra, times the rest, plus derivative of the last, times the rest, plus derivative of the middle times the other 2 bits. And now what we have here, well, here is just h times the energy eigenstate, but you know from the eigenstate equation that that's just the eigenvalue, which is E times this. Here it's the same. So this should be E star, but because the Hamiltonian is Hermitian, this is a real number, so it's going to be E again. Okay, so we just reorganize, we just take these two terms and we write it like this. So this is E times the derivative of the first times the second plus the first times the derivative of the second. Okay? Plus the other term is still left over here. Okay? But this thing is precisely the derivative of these two, right? Because it's derivative of the first times the second plus the first times derivative of the second. That's just a derivative of the product. So that's what we have here. So what we have there is the derivative in order to lambda of this inner product. But because this is the same state and is normalized, this is 1, right? The inner product is 1. And 1 is a number that does not depend on lambda in any way. So then this term is 0. So this derivative is 0, which tells us that in the end, the result is that this derivative is just given by that term there. Okay. Even if this state itself does depend on lambda. Good, so this was the proof of this theorem. And that's it. This theorem you can use in many other problems. So you can also use it in 1D problems, for example. This is completely general. You can use it for discrete systems as well, and so on. So let's just recap on what we've done so far. So we start with the hydrogen atom, which had this potential. It was the kinetic energy of the electron and the potential energy that it feels from the proton in the center, right? And we assume that the proton is fixed, so we don't have to worry about this. Good. Then we saw that the energy eigenstates, they depend on 3 numbers. One is n, which will give us the energy, and that's called the principal quantum number. We have L, which is the total angular momentum, and then we have m, which is just the z component of the angular momentum. Right? We saw, for example, that the average size of the atom is given by a n square if we are in an eigenstate of energy n. And then we saw that there's this restriction, this relation between the different quantum numbers. So L must always be smaller than n. So these are kind of the possible states. And for each L, there are well, 2L plus 1 values of n, right? So these are all the states. And then we saw that these have names in atomic physics. So the ones with angular momentum, total angular momentum 0 are called the s orbitals, and they have this characteristic that they're just flat. Then we have the p orbitals when L equals 1. If L equals 2, they are called the d orbitals, and f, and so on. Yep. Okay, we saw that the energy levels depend only on n squared, and they increase. And I told you that this is corroborated by experiment. So this is confirmed by experiment, right? This is one of the things that really gave quantum mechanics a kick, was the fact that, well, it was a successful theory that really predicted the structure of the hydrogen. So how can we detect this? What kind of experiments can one do? Well, the idea is that if you have an electron that's in an excited state and you leave it for long enough, it tends to relax. It wants to go to the ground state. Yeah. And because there's conservation of energy, it needs to release this difference of energy somehow. And the way this happens is by releasing a photon. So it's like a spontaneous creation of a photon that goes, which has the same energy as this gap here. That's just how the physics works. And the energy of the photon is proportional to the frequency of the photon. And the frequency of the photon is just frequency of light, it's just the color of the light. It's given by this this relation here. Where this nu is the frequency and D is the energy, and this Planck constant as per usual. So one experiment that can be done is to kind of excite an atom. You can just shoot light in many frequencies, for example, shoot white light at it, just many frequencies, the electron gets excited, and then eventually when it relaxes from all the different levels, right, it will emit photons of different frequencies, and you just observe these frequencies, right? You literally just look at the color of the light. Of course, there's more complex ways to measure these things, but you can see that it was already possible to do this kind of experiments even 100 years ago. You don't need super high-tech equipment for this. Okay, but this was just the hydrogen atom. So what about other atoms? Other atoms means well, more protons in the nucleus, sometimes neutrons as well, which have no charge. But if we take our approximation that, well, the nucleus is much heavier, it's just sitting there, then that's not such a big deal. However, what you then have is several electrons, and all of these electrons can interact with each other, right? So we have, because they have the same charge as the charge of one of the protons. So not only you have this interaction from the center to the electron, but also between the two electrons. Yeah. So this becomes a very complex problem. In fact, it's analogous to the many-body problem, which you might have heard about. This is if you have many planets, for example, orbiting a sun, and you want to compute their orbitals, even in classical physics. And this turns out to be very hard differential equations that we don't know, we cannot solve analytically, which means we need to solve them numerically. And a big bunch of computational physics is just finding clever ways, and also computational chemistry is also for different types of molecules and atoms to find the right approximations to make all these problems treatable by a computer. So there are several courses at ETH about this if you want to do it. And it's also, as we mentioned a few times, one of the hopes that quantum computers will be better than classical computers at solving this kind of problems. Okay, there's something we totally skipped so far, which is what about the internal spin of the electrons? When you talked about spin first, one of the examples I gave was said, well, a spin half particle is, for example, an electron that can be pointing up or down. Right? So if we were to be more precise, then the whole Hilbert space of the electron is the position in space. So this kind of 3D coordinates that can be written in Cartesian coordinates or sphericals, like here. Tensor, the spin degree of freedom, so this internal spin degree of freedom, right, which is the corresponding to S1/2 to spin 1/2, which tells me that then the state of an electron, so a total state here, can be expressed in a basis where, so you sum over all possible quantum numbers for the orbital degree of freedom, right? So you have N, L, and M. These live in the 3D space. Tensor, a basis for the spin, which is S going from -1/2 to +1/2. Right? Sorry, not S, N, S. Give me a second. NS. Okay. So it's the Z component of spin. Right? And what does this tell us? Well, in order to see what these look like, then we need to add spins like we did before. So we leave the radial component to the side for a moment, and then we just have this LM. And we need to do the tensor product with this, so we know how to add spins from the previous lectures, which means that we get a new kind of quantum spin number, J. This is going to it's usually called J, and that's a combination of L and S, and an Mj, which will be a combination of this M and Ms, and so on. Okay, so we'd have to consider this as well. And why is this important? Well, because the Hamiltonian, so far we looked only at the Hamiltonian on this 3D space, right? Which was this thing that we saw before. But turns out there's also a component which is much, much, much smaller, which is why like what we saw before is a good approximation. But there's a much smaller term, which is an interaction between the orbital angular momentum and the spin angular momentum. And one way to get an intuition for why there could be such a term, well, it takes a while to understand, but first of all, think of the spin as being a little angular momentum as well, and angular momentum interacts with, or think of the spin as being a little internal magnetic moment as well, something like this. And now think in the same way that we can see the solar system from the outside, and we see the sun stopped in the middle and the earth going around, but we can also go to the frame of reference of the earth, which is what we do in our everyday life. And what we see is the sun kind of going around the earth, right? So in the same way, you can go to the reference frame of the electron. Okay, so even if in reality we have something like this, the electron going around the proton, from the reference frame of the electron, the same way that we see the sun going around us, we can see the proton going around the electron, right? And of course, that's in the same way that the apparent velocity of the sun in the sky depends on the actual velocity of the earth around the sun. The apparent speed and angular momentum of this proton depends on the actual, on these numbers that you computed before, on the actual orbit of the electron. And then the idea is that this is like seeing a charge going around me, causing a magnetic field. And this you know from basic electronics lectures, or from electromagnetism or basic physics lectures. So if you have a charge going around, this creates a little magnetic field, and the spin of the electron reacts to this magnetic field. That's kind of the intuition for this, the very classical intuition for why there's such a term. Sorry. Good. Then there's other things there's other corrections that we can add as well, which result in what is called the fine structure of the hydrogen atom and the hyperfine structure of the hydrogen atom. One is just put relativistic corrections, because although these particles are small, but they go quite fast, so you need to take into account the speed of light and so on. So you can do a little relativistic correction. And the other one is to think, well, the nucleus also has a spin. Okay, so there's actually one more component that we have to put in everything. So one more Hilbert space, which is the Hilbert space of the proton spin in the middle. And this will also cause a little change here in the total Hamiltonian. So overall, if you have instruments that have enough precision, you see not only energy levels that depend on n. So here we have the energy, and here we have like the eigenstates corresponding to n equals 1 and n equals 2. But you also get a splitting. So this is just a splitting from here, from the internal spin, this term that we saw here. Then it gives us a splitting on the j. So depending on whether this is up or down, essentially, then you get this splitting there. And then you get a further splitting in energies, which is even smaller. That will depend on the spin of the proton inside the nucleus. And if you have enough precision in measuring the frequency of the photons that come out, then you can actually observe all of these levels. Which is to say, we told you a story in very broad terms. In fact, you have all the tools you need to to do most of this correction, right? Maybe not the relativity one, but all the others. If you think about it for long enough, you'd be able to do it, or at least you should be able to follow such a derivation, right? But this to say, it's reality is always more complicated than the stories we tell about it, right? Okay. So that was it. With this, we kind of finished everything. The only thing missing is to look into heat engines where we put everything in. So both the Lindbladians and also the work extraction, and see it running in real time. So this will be an extra lecture that I'll upload at some time, and it will definitely not be in the exam. Okay, so that's all for now. So thank you for watching. If you're not taking the course and just watching this on YouTube, I will upload the lecture notes when they're finished to my website, and I'll make a link on in the description, so check again in a month or so. And if you are taking this course and you enjoyed it, then I recommend you take the advanced topics in quantum information theory course, which you should be okay with, and also the QIP1, quantum information processing, which is essentially a quantum computing course. Okay, and that's all. Thanks and good luck for the exam. Ciao.